Okay, we are looking at limits, and we're talking about the formal definition of the limit. And the idea here is we want to construct a delta. But this is our definition up here of what the limit is, and of course, you know, f is a function, and we're on some open interval. But anyway, this is our limit down here, and to figure out how to get 5, well, first thing I do is I plug 2 directly into all this, and I end up getting 0 over 0. And that's kind of bad news, but we can figure that out. And that is by what we're going to do here is we're going to factor the numerator. Now, I made a comment earlier in some earlier videos before this one, and that is if you've never seen the limit before, I suggest that you go look at the section evaluating limits analytically, and maybe first numerically and then analytically, because that kind of tells us how we're getting here to 5. But I'm kind of speeding through that process. And anyway, so we got 0 over 0, so what I'm going to do here is I'm going to factor the numerator, and I can cancel terms out, and now we're left with this new limit. Even though this new limit here is still going to be equal to our original limit. And of course I do the direct substitution, I plug 2 directly in, and I get 5 out. Now this stuff you've been seeing over here on the right hand side of the screen is the graph. Let's take a look at that. Okay, so this is the graph, and yes, it is a straight line. This is the graph of x squared plus x minus over x minus 2. And if you're not familiar with graphs, you might be wondering, why in the world is this a straight line? Well, that x minus 2 down in the denominator, which is causing a missing point here, and right at 2. Okay, so the x plus 3, right, this would be a totally continuous line without the hole if it was just x plus 3, but it's not. And so there's a missing point here in the graph. Now the distinction between evaluating a function at a particular x value, for example f of 2, well, remember we plugged 2 directly into the function, we got 0 over 0. And so we don't really know where this hole is located. But if we use the limit concept, right, we can actually find where this hole actually lives here on this line. And that's the kind of the distinction there between evaluating a function at a particular x value or actually finding the limit, okay, as in this case x approaches 2 of the function. And of course you can see here that the y value associated with this x value is 5. Okay. So now let's try to find a delta. All right. And so we have got it set up, and of course we work backwards. Remember, we're taking this, drop or simplify it. Right, 3 minus 5 is -2. Drop the absolute value signs, and so we're left with x minus 2 is less than epsilon, and then taking the 2 over to the right hand side. So we're saying that the x value that we choose has to be less than epsilon plus 2. Now what we're claiming now is or what we've shown, I should say, is that our delta, which we were looking for, is actually equal to our epsilon. Right, so here's our 2, and we want to go out to the right hand side a 2 plus epsilon, and that means that we can come back in this direction a 2 minus epsilon. Now of course you noticed I just did the x minus 2 is less than epsilon. Remember, there's another one, and that's x minus 2 is greater than negative epsilon, and when you solve for x in that problem you get x is greater than 2 minus epsilon, right? And actually this kind of looks a little bit greater than this side here, just maybe slightly, I don't know. Okay, both these intervals are supposed to be equal right here. Alright, so that was pretty easy actually to construct our delta. Now the reason that we can go over this distance and it's equal to, right, this distance here is because it's a straight line. It's a straight line, and not without getting into the details